6.2 Sum, Difference, and Double Angle Identities. Do the investigation on page 299. Questions 1 to 5. Include tan in question 5 and then come back and continue this video. Now if you're done, let's go over it, or if you don't have the textbook, let's try it. We're going to make any rectangle. And we're going to draw this right triangle inside the rectangle. The hypotenuse of this right triangle is 1 unit long. We're going to call this angle alpha here and this angle beta. And that's it. So this could be any arrangement. This triangle just needs to be a right triangle. It needs to hit anywhere on this side BC. And F is just some point on DC that will make this a right triangle. Let's try to fit these in to this diagram here. First, I'll spread them out. Now we have to start inside with the right triangle. It has a hypotenuse of 1. And this angle beta and this side AE gives us cos beta is equal to the adjacent side AE over the hypotenuse, which is 1. Now, the 1 really doesn't matter, so cos beta is essentially side AE. So we will label it cos beta. Let's do that again, except with this opposite side. Do the same thing. Sine beta equals EF over 1. So sine beta is this side here. Next, we'll do this triangle at the top. It's also a right triangle because it makes use of one of the rectangle's vertices. So this one could be cos alpha, using this angle here, is equal to the adjacent side, which is AB, divided by the hypotenuse, which we've now labeled as cos beta. Do some algebra, and we've got that side AB is equal to cos alpha times cos beta. So we can label that side as cos alpha cos beta. Now let's go to BE. It would involve sine. So we could say sine alpha is equal to BE over cos beta. Do some algebra. We get BE is equal to sine alpha cos beta. And that is right here, so we could label this side of the triangle BE as sine alpha cos beta. Let's get some angles on here. This angle right here would be 90 degrees minus alpha. This angle right here would be 180 degrees from this straight line minus 90 degrees from this right angle taken up here, minus this angle, so minus 90 degrees minus alpha. And 180 minus 90 is 0, and all you're left with is alpha. So if you couldn't tell, this angle right here is also alpha. Let's go down. This one is 90 degrees. This would be 90 minus alpha. This one, 90 minus beta. And a right angle here. This one would be alpha plus beta. You can get that by taking 180 degrees, subtracting these two angles, you'll get alpha plus beta. It's also this angle here. This line, since we drew a rectangle, is parallel to this line, so these are actually opposite interior angles, so they are the same. Let's find side CE. That one we can use alpha, so that would be an adjacent side. Cos alpha is equal to the adjacent side, CE, over the hypotenuse, which is sine beta. And then rearranging, we get that CE is cos alpha times sine beta, which would be this one. Next, we can do the same for side FC. So FC would be also using alpha here. Sine alpha equals opposite, which is FC, over hypotenuse, which is sine beta for this triangle here. And rearrange this. That'll be FC is equal to sine alpha times sine beta. And that'll be this guy right here. Let's work with the last triangle. We want side DF, and we have this angle here, alpha plus beta. So this one would be an adjacent to that. So cos alpha plus beta is equal to the adjacent side DF over the hypotenuse, which is 1. So cos alpha plus beta is this side here. Last is side AD, and that one would be a sine. It would be opposite of this angle, so sine alpha plus beta is equal to side AD is the opposite over the hypotenuse, which is 1. And there we got the label for that side. Now the great thing about this diagram is that we get different measurements on opposite sides of our rectangle. So on the top we have cos alpha, cos beta, and on the bottom we do not. We have two pieces. On this side we have sine alpha plus beta, and on this side we have two pieces to make that up. And we can actually make an equation with this. So we could say the top is cos alpha and cos beta, and that equals these two pieces, cos alpha plus beta and sine alpha times sine beta. And this is an identity. We probably want to solve it for cos here. So cos alpha plus beta is equal to this side, cos alpha times cos beta minus sine alpha times sine beta. That gives us an interesting sum identity, as in addition. Let's do the same thing with this side here. So we have sine alpha plus beta, and it equals sine beta cos alpha plus sine alpha cos beta. And that is another sum identity. So we're going to use those in the future. These are the three sum identities. We've got sine alpha plus beta, which is the one we just worked out, and cos alpha plus beta, which is the other one we just worked out. And we can take this one and divide this one and do some rearranging and get tan's sum identity. Now let's use these to find the difference identity, sine alpha minus beta. All we have to do is add a negative beta. Essentially that's the same thing, but once we add, that means we can use this sum identity here that we've already worked out. So here it goes. We've got sine alpha plus negative beta is equal to sine alpha cos. See, before it was beta and beta, and now it's negative beta, so we put negative beta everywhere where there was a beta. So cos negative beta plus cos alpha sine negative beta. Okay, now that looks all good. The next step, we're going to do two things. We're going to simplify this plus a negative and just write minus because that's really what we wanted. The next thing, we're going to remove this negative sign, and when it disappears, okay, and this negative sign inside the sign, it comes out and moves in front. Okay, so why do those two things happen? When we have angles in standard position, our coordinate on the unit circle is cos theta sine theta, and this represents the x value of our coordinate, and this represents the y value. So if we move this the same magnitude forward as we do in the negative direction, then The first thing we notice is our x-coordinate is exactly the same. So that answers the first question. When we have cos of negative theta, it actually equals cos theta. The next one is when we look at the y's, our y value, or our sine value here, is exactly the same magnitude, but it's just this one is negative. So that's why our sine of negative theta is negative sine theta. Now for tan, we have these ones figure out already, so we'll break tan down into sine and cos. We know that sine's negative, sine just comes out, and cos's cancels. And sine theta over cos theta is just equal to tan theta. So we see tan works just like sine. The negative sign comes out. Now, flipping back to the previous slide, we see why cos's negative sign here canceled out and just disappeared. And sine of negative beta, that's the negative came out in front, and then we ultimately moved it out into the front of this whole term here. So this would be sine's difference identity, like that. Take a few minutes, find cos and tan's difference identity. Cos's sum identity is cos alpha cos beta minus sine alpha sine beta. We just need to put a negative beta in here. So same procedure as we did before. Plus a negative beta. So everywhere where you see beta, let's put a negative beta instead. And this one's pretty easy. We get that cos alpha minus beta is equal to, remember this one cancels out, so we're just left with cos alpha cos beta again. And on this side, the negative side comes out, so let's bring it out and all the way and join it with this one, so it'll be plus sine alpha sine beta. And there is cos's difference identity. So here's our three difference identities. Now we want to find a double angle identity, which means 2 alpha. So we're going to replace the beta with another alpha, so we get alpha plus alpha. And we're going to use sine's sum identity. And just everywhere where we had a beta before, we're going to put an alpha. And that will give us sine 2 alpha is equal to 2 sine alpha times cos alpha. You can try cos 2 alpha and tan 2 alpha. And you should end up with these three double angle identities. Now we want to take cos's double angle identity and write it without sine squared alpha here. Now when you see sine squared alpha, hopefully you remember the Pythagorean identity. Sine squared alpha plus cos squared alpha equals 1. So that means that sine squared alpha is 1 minus cos squared alpha. And I can sub out the sine squared alpha with 1 minus cos squared alpha. This is now cos squared alpha minus 1 plus cos squared alpha, which means I've got 2 cos squared alphas minus 1. And that's a new cos double angle identity. One more time, let's write cos's double angle identity without cos, and you do a really similar thing as this example here. So cos 2 alpha, and instead get rid of this guy with 1 minus sine squared alpha. And the sine squared alpha would still be here instead. And thus equals 1 minus 2 sine squared alpha. And that would be a different way to write cos's double angle identity. And it's special, it gets 3 different ways to write it on our formula sheet. Let's simplify these trigonometric expressions. The first one, what is cos pi over 3? Well, that would be 1/2. And then we square it. And what's sine pi over 3? Well, that would be root 3 over 2. And we also want to square that. Now, 1/2 squared is 1/4. And root 3 over 2 squared is 3 over 4. And 1/4 minus 3/4 is -1/2. But there's another way to do that. Using the identities that we just discovered, cos squared alpha minus sine squared alpha should look familiar. Because we just did it, it's cos 2 alpha is equal to cos squared alpha minus sine squared alpha. So we can just use that to change this. So this is really, alpha is pi over 3 in this question. So this is really cos 2 times pi over 3. Now I only have one thing to find, and cos is 2 pi over 3 is -1/2. Let's try this next one. This next one is awfully long, and I don't know what 48 and 18 is off the unit circle, but I do recognize this as tan's difference identity. So we'd say tan alpha, this one would be alpha, this one would be beta. So tan alpha minus beta, and that would just be 30 degrees. And now I do know tan of 30 degrees, 1 over root 3. What are the non-permissible values of this expression? We're just looking at sine 2x here, and it cannot equal 0. Now that means that 2x cannot equal 0 or pi or 2 pi and so on, because that's what makes sine 0. And divide both sides of this by 2, so you get x cannot equal 0, pi over 2, pi, and so on. We could use an identity, though, to simplify the denominator. So sine's double angle identity. So if we had sine 2x, that would actually equal 2 sine x cos x. And now we just want sine 2x cos x not equal 0. And this might be a lot easier to work with. We have sine x cannot equal 0, cos x cannot equal 0. That would be the x and the y-axis, so just all our quadrantal angles. So x cannot equal pi over 2n, where n is an integer. Now let's simplify this. In the numerator we have 1 minus cos 2x. Now that's the double angle for cos, and we can use one of the double angle identities. Unfortunately, there's 3 we could use. I like to use one that will get rid of this 1. So I'm going to use 1 minus 2 sine squared x. No more double angle identity. Next, in the denominator, same thing, but this one's easy. We only have one choice. It's the one we used here, 2 sine x cos x. Now we can multiply in the negative here, so 1 minus 1 plus 2 sine squared x, and the denominator will patiently wait. And then 1 minus 1 will cancel. Get 2 sine squared x over 2 sine x cos x. The 2's will cancel, and one of the signs will cancel, numerator and denominator, and I'm just left with sine x over cos x, which is tan x. Mission accomplished. We simplified to one of the primary trig ratios. Let's find the non-permissibles of this. Looking at the denominator, it cannot equal 0. So minus 1 on both sides, and we could get cos 2x cannot equal to -1. Now where does cos have a ratio of -1? That's at pi. So 2x cannot equal pi, or 3 pi, or 5 pi, so on. And divide both sides of this inequality by 2 here, and we get that x cannot equal pi over 2, 3 pi over 2, 5 pi over 2, and so on. Now that was okay. Perhaps it is easier if we use an identity to simplify the denominator first. So let's get rid of cos 2x by using an identity. We'll just say or here. We use this cos's double angle identity, 2 cos x squared minus 1 plus 1 cannot equal 0 because the minus 1 plus 1 cancel out. We can also divide both sides by 2 here, and that just leaves us with cos squared x cannot equal 0 still. Square root both sides, the square root of 0 is 0, so cos just cannot equal 0. And that's a lot easier to do. That's just the y-axis. So x cannot equal pi over 2 plus pi n, where n is an integer. Either way will work. Now let's simplify this down. Sine's double angle identity is 2 sine x cos x. And we'll use the same thing that we did here to simplify the denominator. So the denominator was 2 cos squared x minus 1 plus 1. Minus 1 plus 1 cancels. In this case, the 2's also cancel, so we're left with sine x cos x over cos squared x. And the cos cancels with 1 in the denominator, and we're just left with sine over cos x, and that is tan x. And it's just a coincidence that it was the same as the last question. Using identities, we can find the exact value of other trig ratios that weren't on the unit circle if we can figure out how to make two angles that we do know, add or subtract up to it. So this one's pi over 12. It might be easier to think of this as 15 degrees. Now what two angles do we know we could add or subtract to get 15 degrees? Well, we could do it with 45 degrees minus 30 degrees. So going back to radians here, this is pi over 12, and that could equal 45 degrees, which is pi over 4, minus 30 degrees, which is pi over 6. And if we wrote this with a common denominator, it would be a little bit clearer what we're doing here. So this would be 3 pi over 12, and this would be 2 pi over 12. So you can see that 3 pi minus 2 pi is 1 pi over 12. Now let's rewrite this as sine pi over 4 minus pi over 6. And now we can use sine's difference identity. This is alpha, and this is beta, say, and use the difference identity that we worked out before. That would be sine alpha, pi over 4, cos beta, pi over 6, minus, and these just switch spots, sine pi over 6, cos pi over 4. Now we've written this in terms of everything that we know. We know sine pi over 4, it's root 2 over 2. We know cos pi over 6, it's root 3 over 2. We know sine pi over 6, it's 1/2. And we know cos pi over 4, it's root 2 over 2. Now we can simplify this. We get root 6 over 4 minus root 2 over 4. And probably put it together will look nice. Root 6 minus root 2 all over 4. Now these are different radicals, so we can't combine them here. So this would be our final answer. Now we want to find the exact value for sine 105 degrees. So we need to think of two angles we can combine in some way to get 105. So say you thought of maybe 45 degrees plus 60 degrees. Now they have to be two angles that we know, otherwise this isn't going to work. Now we use sine's sum identity, so that would be sine 45 cos 60, and then sine 60 times cos 45 degrees. And now we know sine 45 degrees, it's root 2 over 2. We know cos 60 degrees, it's 1/2. We know sine 60 degrees, it's root 3 over 2, and we know cos 45 degrees is root 2 over 2. We can combine these, and we get root 2 plus root 6 all over 4. Now you might say, hey, I didn't think of that, or wait a sec, will something else work? Yes, definitely. So what if you thought of sine 135 degrees minus 30 degrees? Well, now we'd be using sine's difference identity. So that would be sine 135 degrees cos 30 degrees, and minus, for the difference identity, sine 30 degrees cos 135 degrees. And now we know all these angles. Sine 135 is root 2 over 2. Cos 30 degrees is root 3 over 2. This is minus. Now we got sine 30 degrees is 1/2. And cos 135 degrees is negative root 2 over 2. So combining the first two terms, we get root 6 over 4, and the negative signs here will cancel, so we'll get plus, combining these two terms, root 2 over 4. And you can see that we ended up with the same thing as the first way, just with the numerator in a different order, but that really doesn't matter. Let's find the exact value for cos 165 degrees. And if you aren't, pause the video and try it yourself. This could equal cos 45 degrees plus 120 degrees. Now we'll use cos's sum identity. So cos 45 degrees times cos 120 degrees minus sine 45 degrees times sine 120 degrees. Cos 45 degrees is root 2 over 2. Cos 120 degrees is negative 1/2. Sine 45 degrees is root 2 over 2. And sine 120 degrees is root 3 over 2. Let's combine up these terms. So we get negative root 2 over 4. And this one will be minus root 6 over 4. We get negative root 2 minus root 6 all over 4. Now again, you may have thought of a different way. That's great. Let's try cos 210 degrees minus 45 degrees. That still equals 165 degrees. This time we'll be using cos's difference identity. So cos 210 degrees times cos 45 degrees plus sine 210 degrees times sine 45 degrees. Now cos 210 degrees is negative root 3 over 2. Cos 45 degrees is root 2 over 2. Sine 210 is negative 1/2. And sine 45 degrees is root 2 over 2. Put these together, we get negative root 6 over 4 and minus root 2 over 4, and that's root 6 minus root 2 all over 4, which is in a different order, but it really is the same thing as the first. Now you may have thought, hey, you still didn't get the one I thought of, and that's fine. I won't do this one, but you could have also done 135 degrees plus 30 degrees, and that would have been a great one, and that would have worked as well. This is part of Trigonometry 6, proving trigonometric identities using all of these identities. Today we talked about the sum, difference, double angle identities. Here's some questions, give them a try, see if you know what you're doing.